Okay, so we're recording. Let's begin. Okay, so before we actually discuss the stationarity test, we need to discuss deterministic and stochastic trends. Okay, so we'll look at that theoretical aspect first, and then we'll discuss the tests of stationarity or unit root tests. Okay, now, given a time series yt, if yt changes by a fixed amount from one period to the next, okay, so if you know by how much yt is going to change from one period to the next, if that change is equal to some constant a naught, okay, then you can iterate forward and then find out a general solution to this particular difference equation. Okay, so let's write this equation number 1, in the form of a difference equation. Okay, so that can be written this way. Now, if you iterate forward one period, okay, then you'll be able to write yt plus 1 is equal to a naught, okay, plus yt, the value in the previous period. Okay. Now, instead of yt, you can just substitute this equation that you had for yt. Okay. So that's what's been done in the next step. So you get 2a naught plus yt minus 1. So if you keep iterating forward this way, okay, if you move on update by one period, then this is what you'll get. Okay. Now, if you keep updating this way and then try to find out the solution for this general difference equation, okay, then this is the form which the general solution to this difference equation will take, a naught t plus yt minus 1. You can try it out for yourselves. If you're not able to follow, just try and work it out for yourself. You'll find that in each period, for example, this is the first period. Okay, so you just have a naught multiplied by 1. Now in the second time period, which is yt plus 1, you have two a naught terms appearing. That's why a naught is multiplied by 2. Now in the third time period, which is yt plus 2, you have three a naught terms appearing, okay, which is why a naught is multiplied by 3. So after t periods like this, there'll be t such a naught terms which will accumulate, and that will be a part of the general solution to this difference equation. Okay, and you'll have the initial value or the initial condition. So here, okay, this equation, I've just written it in the form of that initial condition. Okay, assuming that there is an initial condition which has been specified, using equation 4, you can write the general solution to the linear difference equation. And this is the form which the general solution will take, assuming that y naught is the initial condition for the time period t is equal to 0. Does anyone have any doubts about how we arrived at the general solution? Is it clear to everyone?
Yes, ma'am.
Okay. Now, if you look at equation 5, okay, it'll show you that the solution to that difference equation which we had, which was given in equation 1, okay, is in the form of a deterministic time trend. Now, why am I saying that it's a deterministic time trend? Because you know that a naught is some constant, and you know by exactly how much in each period the value of this time series is going to change. Okay, from the initial value in each time period, it will be changing by the amount a naught. Okay, so that's why we say that the solution to the difference equation, which was given in equation 1, is it in the form of a deterministic time trend. Okay, since a naught is some constant which you know, okay, t will assume various values 1, 2, 3, 4, and so on based on the time period that you're considering. Okay. Now, if we add a stationary component in the form of the error terms to the trend, okay, if you add a stationary component which has moving average error terms, okay, to equation 5, then this is what you'll get, equation 6. Okay. Now, since you've been told that these moving average terms are stationary in nature, okay, so these represent deviations from this linear deterministic time trend. Okay. So these are stationary deviations of yt from the trend. So when we are saying stationary deviations, it means that these deviations from the time trend will merely be temporary. Okay? So in each period, you might find that yt rises above this linear deterministic time trend. I'm circling this time trend here. Okay, now if you're looking at the time trend itself, y naught will give you the intercept and a naught will give you the slope of the time trend. Okay, so you'll be able to plot it on a graph. It will be in the form of a straight line since t is raised to the power 1. Okay, so your linear deterministic time trend will be in the form of a straight line, and you'll notice that in each period yt may rise above or below this time trend. Okay, but these deviations from the particular time trend will be temporary, and largely you'll find that yt is a mean reverting process. It keeps moving back towards the trend line. Okay. So such a process, if yt is such a time series, it is called a trend stationary time series, or the model is said to be trend stationary. Okay, because whatever deviations are there from the trend line, they will only be transitory or temporary. Okay. Since the error terms that you're adding are stationary. Any doubt so far? Anything that you did not understand? Yeah, I'll continue. If you ever have a doubt, please stop me and ask questions. Now, instead of the change in yt being some fixed amount, okay, suppose the expected change in yt is a naught units. Okay. So delta yt is equal to a naught plus et. Okay, that's given in equation 7. Now et is a white noise error term, which means that the mean of et is equal to 0 and has some constant variance. Okay. Now yt, okay, we expand this itself, equal to a naught plus yt minus 1 plus et. Now, if you keep iterating forward, just repeat that whole process that we did in the first page. Okay? Keep iterating forward one step. Okay? Then you'll get equation 8 okay, in the second time period, equation 9 in the third time period. So the form which the general solution to the first order difference equation, which is given in equation 7, will take is this. Okay, you will have the initial condition plus these error terms. Okay, the sum of these error terms up to time t. You will find that in each period you're adding one additional error term. Okay? And you'll have an accumulation of these a naught terms as well, the constant terms. Okay, so you will get equation 10 as the general solution to the first order difference equation given in 7. I'll just give you a minute to go through it. Okay, now if you have gone through the equations, I hope you have understood how we reach the general solution of this first order difference equation. Now, if you look at the general solution itself, you can think of it as being made up of two parts. Okay, one is this linear deterministic trend component, okay, a naught t. Since a naught is some constant, you know that in each period, the value of yt is going to change by a naught. Okay? And the other component of yt, okay, if you look at the general solution, is these two terms, the sum of these two terms. So these two terms are something known as a stochastic intercept term. Okay? So y naught is the fixed component of this stochastic intercept term, but because of ei, okay, or the error terms, you will find that there are deviations. The intercept term won't be fixed like how we saw in the previous situation. Here, instead, the intercept value will keep changing. Okay? Now, in addition to this, you will find that these EI terms, the coefficient attached to them is 1. Okay? There's no specific coefficient given, so you know that the coefficient attached to each of these error terms is 1. So because of this, the effect of any shock which is impacting yt, it will be permanent in nature. Okay? The effect of those shocks will not decay or decrease with time. Instead, if you look at the first case, okay, since the error terms are stationary, okay, these moving average terms which have entered the equation, you know that they are stationary in nature. So because of this, you know that the impact of past shocks will begin to die out with the passage of time. Okay? But here in the second case, you'll find that since the coefficient attached to each of these error terms is unity or 1, so the effect of these shocks will more or less be permanent. Okay? They will not decay over time. So because of this, yt is said to have a stochastic trend. Okay? And in this case, since each error term leads to a permanent, although random change in the conditional mean of the series, you will find that it will be a little harder to make yt revert back to the mean. Okay? Since the effect of each of these shocks is permanent, it's very unlikely that yt will display mean reverting behavior and return to the conditional mean of this time series. So we looked at two particular cases. One is where the change in yt is some fixed amount. Okay? So that is the case where the time series has a deterministic time trend. Now here, if you take the expected change in yt, okay, is a naught units. Since the expected change in yt, if you take expectations here, et will disappear. Okay, since the mean of et is 0. So the expected change in yt is here a naught units. So because of this, you will find that there's a stochastic intercept term which has crept into the general solution for the difference equation. And because of this, the time series yt displays what is known as a stochastic trend, where the effects of shocks do not die out with the passage of time. So these are two types of trends. Okay, you have a deterministic trend and a stochastic trend. Now let's look at a specific case and try and understand how we go about testing for stationarity and so on. Okay, so if you understand these models, then you'll understand the logic behind the unit root tests and stationarity tests that we conduct. So for a random walk model, okay, first just take this equation, then we'll look at the random walk model itself. So here if delta yt is equal to a naught plus et, okay, the same form that we saw earlier, okay, on the previous page. Et is a white noise error term here. Okay, so you know that mean of et or expectation of et is equal to 0 and variance of et is some constant. Okay, and covariance between et and its lags is equal to 0. Okay, so those are properties of a white noise process. Now consider the special case where a naught is equal to 0. Okay. Now in this case, the equation in 1, it will simply reduce to delta yt is equal to et. Okay, this is actually epsilon t, but I find it easier to say et, so I'm saying et. Okay, if et is also there, then I'll switch to epsilon t. Just keep that in mind. So delta yt is equal to et here, or if we expand this term and bring yt minus 1 to the right hand side, we can write it in the form of a first order difference equation. So now equation 2 is the random walk model. Okay. So if you remember, I've discussed this earlier when I showed you an Excel sheet. I generated some random numbers to represent the error terms, and then we looked at different time series based on the value of the first order autoregressive coefficient. Okay. So if you remember that part, in that context, I had discussed the random walk model, which is where the first order autoregressive coefficient, it has a value of 1. Okay, so if you have a1 here, the value of a1 is equal to 1. So this represents a random walk model. Now the name of the model itself comes from the fact that if you want to guess or predict the value of yt, then your best guess for the value of yt. For example, if you take expectation yt, you're going to get yt minus 1 there. Okay, since this term will disappear. So your best guess or your best prediction for the value of yt is going to be the value of yt in the previous period. Okay? So you cannot basically systematically make profits or systematically profit from guessing the value of yt, because you know that your guess will most likely not be accurate, because yt will deviate from yt minus 1 by some error term, okay, which is random. So that's why it's called a random walk model. Now, if you look at the walk of a drunkard, okay, a man who's drunk, you'll find that he keeps walking around in a very haphazard way. He doesn't walk in a straight line or uh, in a very logical fashion like how we normally do. Okay, so you'll find that you probably will not be able to predict where he is going to place his feet next. Okay, so that's where the name of the model comes from, the random walk model. Now, given the initial condition y naught, okay, the general solution to 2 may be written this way. Okay. So if you want, you can take a minute and write the general solution. Okay, so if you keep iterating forward from this point, if you take equation 2 and keep iterating forward, okay, then this is the general solution that you'll find. Would you like to take a minute and derive that general solution? Have you all understood, or would you like to stop and derive the general solution? Okay, I'm guessing that you have understood or you're not listening. So anyway, let's proceed. So the general solution to equation 2, the difference equation given in equation 2, can be written this way. So now if you take the expectation of yt, okay, so it will be equal to y naught. Okay, since expectation of et, all these ei terms is equal to 0. So expectation of yt in every period. So even if you take expectation yt minus s, it will be equal to some constant y naught. Okay. So the mean is constant. So one condition for stationarity is satisfied.
Ma'am, I have a query.
Yes.
Ma'am, you said that random walk theory is difficult to predict. Won't that be a paradox in itself that we are trying to predict a path for random walk?
Uh, I'm not saying that random walk is not predictable. I'm saying that if yt, a particular time series, follows a random walk or it's a random walk process, then it becomes very difficult to predict the value of yt one period ahead.
Ma'am, can we say that, say, let's say, suppose a movement of a stock is a random walk?
Hmm. Yes, okay. So I don't know if you all have already studied this. According to the efficient market hypothesis, it should not be possible to predict the value of a stock for the next period. For example, if I'm trying to predict the price of a stock tomorrow, I should not be able to predict it, because if stock prices follow this random walk, then the market is efficient. Okay? So you will not be able to systematically make profits by guessing the price of the stock, basically. Okay, so that is the logic behind that particular theory, efficient markets hypothesis. I think we'll be covering it later. Okay, once we finish the application of time series techniques, we'll be discussing that.
Okay, ma'am, thank you.
I don't know if I answered your question.
Ma'am, I got to know about it. Even my concept regarding time series are bit muddy. I'm learning as we go. So,
Okay,
but your answers solved my query, ma'am.
okay, okay. So, yeah, where were we? Yeah. Again, if you look at equation 3, okay, you are encountering the same problem that we saw in the case of the stochastic trend. Okay, so here, since each of these error terms is entering with a coefficient of unity, Okay, so you'll find that each of the error terms has a permanent or non-decaying impact on the time series yt. Okay? So the effect of these shocks is not going to die out with the passage of time. Okay? So now if you predict the value of yt one period ahead, okay, then you'll be taking expectation of yt plus et minus 1, et plus 1, okay, since yt will be the value in the previous period. Okay, so here you'll get expectation of yt plus 1 is equal to yt. Now similarly for yt plus s, again you get expectation of yt plus s is equal to yt for all s which is positive. Okay. So if you're trying to predict future values of yt, the constant value of yt is the unbiased estimator of all future values of yt plus s. Okay. Now an ET shock will have a permanent effect on yt, which will be reflected in the forecast for yt plus s. So how will it be reflected in the forecast? If you find out the variance of yt and yt minus s, okay, you will find that the variance keeps changing with the passage of time. So here, if you calculate the variance for yt itself, the variance is dependent on time. You get the value t into sigma square, okay, for variance of yt. Now for variance yt minus s, okay, you'll find that the variance is t minus s into sigma square, since there are t minus s of these et terms over here, okay, or error terms over here. So because of this, the variance is time dependent. Okay? And as you move further and further into the forecast horizon, for example, if I calculated variance of yt plus s, then here I would have had t plus s sigma square, right? Okay, so I would have had s additional error terms. So the variance would have increased by that much, okay, by a factor of t plus s.
Ma'am, can I interrupt a little?
Yes.
If you just go back before the equation 5, the expected value you're talking.
Yes.
Yeah, so the ET of yt plus 1, are you trying to say that the expected value in time period t equals yt, is it?
You're talking about, I'll just point my
The
cursor,
subscript, yeah, the
this
subscript
equation.
of t for the expected value.
Hmm.
Is it?
Okay. Here we are taking the expectation at time t. So we are uh, basing our prediction on all the information that is available to us about this time series up to time t. Okay, so all the values of yt up to time t that are available to us, we are basing our expectation on all that information which is available to us up to time t. That's why it has this subscript t here.
Yeah, exactly. That's what I was trying to figure out. So basically what you're trying to say is, if there is a particular shock in let's say a current period,
Yes.
and we are asked to estimate the stock price in t plus 1. So as per whatever efficient market hypothesis, we say that the best estimate is the today's value itself after the shock.
Yes, yes, correct.
Yeah, thanks.
So because of this,
Is there any way that we can predict shock, like say it's a cyclical or something?
you want to predict the nature of the shock itself, is it?
Ma'am, because shock, there will be shock in a given lifetime. That is for sure, that we can assume safely. But let's say economy like goes through the cycle of depression, recession, boom, bust. So is it possible that to will be able to predict shock, or is it completely random walk, ma'am?
It is random in the sense that these error terms, they are supposed to be random error terms, right? So you can't actually predict the value, but they are drawn from a particular distribution, okay, which has a mean, zero, and variance is some constant. We usually assume that it's drawn from the normal distribution, but it will still be random. Okay, you won't be able to predict exactly what the value of the shock will be.
Ma'am, can we say that the current COVID situation is a random shock?
Yes, yeah.
Thank you, Han.
Okay, so coming back to this, so if you look at the variance, suppose I had taken variance of yt plus s. Okay, so there I would have got the value of the variance as t plus s sigma square. Okay, so you can see that the variance is time dependent. Okay, since the variance of yt is not equal to the variance of yt minus s, again it will not be equal to the variance of yt plus s. And what you'll notice is that the variance increases as the forecast horizon increases. Okay, so the variance of your prediction of forecast, that will keep increasing with the passage of time, and you will not be able to forecast with much certainty. Okay, particularly for a random walk, any forecast has some element of uncertainty, but here it will keep growing and growing over time. Okay, so just remember that the mean is constant for a random walk process. So one condition of stationarity is satisfied, okay, for a weakly stationary time series. But the second condition, that the variance should be constant or finite, okay, that is being violated here. Now, if you look at the covariance between yt and yt minus s also, okay, here you will find that the covariance is a function of the lag here. Okay, it depends on yt minus s sigma square. Okay. So for a random walk process, if you want to calculate the covariances, autocorrelation coefficient, okay, you will take the covariance or autocovariance of at lag t minus s. Okay. So if you're taking it at lag s, okay, you'll take the covariance at lag t minus s and then use these two here. Okay, these are the variance at, since you're taking the square root of variance, it will be the standard deviation. Okay? So the standard deviation of yt at time t and t minus s. Okay? You'll be multiplying those. This is the usual formula for correlation, for calculating correlation coefficient. Since the variance is not constant, you'll have to take the standard deviation at time t and t minus s. Okay? So if you're calculating the autocorrelation coefficient here and you plug in those values which we calculated earlier on the previous page, okay, it will reduce to this. I'll just give you a moment to go through this again. Okay, so what you find from this, okay, from these two, is that the variance is dependent on time, it's not constant. The same with the autocovariance. Okay, so because of this, if you look at the autocorrelation function for a random walk process, okay, suppose your lag value is small. For example, just think that s is small here, okay, and t. Just think that you have a large sample size. Okay, so let's say that t is some large number and s is a small number. Okay? So t here is large, s is small. So for very small values of s, you'll find that the autocorrelation coefficient is equal to 1. Okay, and as s becomes larger, okay, as the lag value increases, you'll find that the autocorrelation begins to diminish slowly. Okay, now for an ACF with if you have an ACF for a random walk process, okay, so there will be a slight tendency to decay as s keeps increasing. You will find that slowly it begins to show some sort of decay. Okay? And as a result, it will not be possible to use the ACF to distinguish a unit root process and a stationary process with an autoregressive coefficient close to unity. Now, the reason this is being said is if you have a stationary time series, just remember what we had discussed for the ACF and PACF, how you identify a stationary ARMA model. Okay, so in those cases, we had said that in the ACF, you will see a sharp spike at lag 1 or there'll be spikes up to lag p and up to lag q, and then there'll be a decay. Okay, so it will decay quite rapidly there after reaching lag q. But in the case of a random walk process, there will be a slight tendency to decay. Okay? For a stationary process, it decays very rapidly once it's reached lag q, if you look at the ACF. But for a random walk process, it will show some slight tendency to decay. So that might confuse you. Okay? So if you have an AR process where the autoregressive coefficient is close to unity, okay? So there also you'll see a similar pattern that up to lag q, you'll find that there are spikes, and then after lag q it begins to decay, but the decay will be quite slow. Now, even for a random walk process, which is a non-stationary process, why is it non-stationary? Because the variance is dependent on time, even the covariance is dependent on time. Okay, so two conditions for stationarity are violated by a random walk process, so it is a non-stationary time series. So even for a random walk process, you'll notice a similar pattern that there'll be slight tendency to decay. So if you look at the ACF of a random walk process and that of a time series which has an autoregressive coefficient which is very close to 1, okay, both will look very similar, and by looking at the ACF, you will not be able to distinguish is it a stationary time series or a non-stationary time series, or a by which I mean is it a random walk process. In the case where the autoregressive coefficient is very close to 1 but still less than 1, it's actually a stationary process. Okay? Remember when we were discussing the AR1 model, we imposed the condition that the absolute value of A1 should be less than 1, and that helps us to show that that particular time series is stationary. Okay? So by looking at the ACF for a random walk process, it might confuse you because even a time series which has an autoregressive coefficient close to 1 will display a similar sort of ACF. Okay? So in order to test whether it's a random walk process, whether there is a unit root, you cannot rely only on the ACF. That's why we'll be discussing tests of stationarity a little later on. Okay? Now, if you augment this random walk model with something known as a drift, okay? So in this case, let the change in yt be partially deterministic and partially stochastic. Okay? So this is the case of the stochastic trend that we had discussed earlier. You'll find that the same sort of equations are appearing here. Okay? So if you add to that simple random walk model that we saw earlier, okay? So this random walk model, if you add an intercept, okay, which is called a drift term. So here we are adding this drift term A naught, which is basically the intercept. Okay. Normally we refer to it as the intercept. Okay. So in equation 9, you have what is known as a random walk plus drift process. Now, given an initial condition, if you keep iterating forward 1 period, 2 periods, 3 periods, and so on, you'll be able to find the general solution for this difference equation given in equation 9. And this is the form it will take. Okay. Since I've already done the derivation earlier, I hope it will be easy for you to follow. Okay, now, if you look at the behavior of yt in equation 10, okay, you can clearly see that yt is governed by two non-stationary components. Now, the reason I'm saying non-stationary is, one, you have a linear deterministic trend. It's deterministic in the sense that A naught is some constant, and you know that the value of yt in each period is going to change by the amount A naught. Okay, that's why this term appears here. So in that sense, it is deterministic because you know that in each period it's going to change by A naught. Okay, but it is not stationary. You can see that the behavior of yt, the mean is going to keep changing over time. Okay. Now, a stochastic trend is also there in this particular time series. Okay. So that stochastic trend component is in the form of these cumulative errors or the summation of the error terms. So if you remember our discussion earlier in the first part of the class, we had said that yt is equal to this stochastic intercept term, y naught plus summation ei, and a linear deterministic trend term. Okay? So here, since the intercept term is stochastic, okay, so although in a particular period, if the error term is equal to 0, okay, then your intercept will be equal to y naught. But otherwise, in general, it will deviate from y naught. It will either be greater than y naught or less than y naught. Okay? So because of this, again, there's a stochastic trend component. And again, if you remember, since the error terms are entering this equation with a coefficient of unity, the impact of each error term will be permanent in nature. Okay? So yt will be affected by these shocks in a permanent way. The effect of these shocks will not die out over time. So in effect, it means that there is no stationary component in equation 10. So if you have a random walk with a drift, it is made up of two non-stationary components. Okay, so the whole time series becomes non-stationary as a result. Okay. So if you look at the mean and so on, okay, when we look for the properties of a stationary time series, if you take expectation of yt, okay, it will be equal to this equation 11. Now expectation of yt plus s will be equal to y naught plus a naught into t plus s. There are s additional a naught terms here, okay, because of the linear deterministic trend here. So the drift means that even the mean is not constant over time. Okay, for a random walk plus drift model, you will find that the first condition of stationarity itself is violated, that the mean is constant. So here the mean is not constant. Okay. But if you take the first difference of this time series, okay, then it becomes stationary. So we'll come back to this part a little later, that taking the first difference makes it stationary. So if you took that first model, okay, the first equation that we had written for the random walk plus drift, okay, and you bring yt minus 1 to the left hand side, you're basically taking the first difference. So in this case, if you take expectation of delta yt, okay, since expectation of et is equal to 0, you get expectation of delta yt is equal to a naught, which is a constant. So first differencing a random walk plus drift model, it makes the time series stationary. Now to obtain the S step ahead forecast for a random walk plus drift, okay, use equation 10 and update by S periods. If you take equation 10, update it by S periods, you will be able to forecast the value of yt plus S. So here again, you will have S additional A naught terms and S additional error terms. So here in the second part, the reason it's been written like this is, if you're forecasting from time t, you're forecasting S periods ahead. Okay, then t becomes your initial value. And from that value, how are you moving forward? That's what equation 14 is showing you. Okay. Similarly, if you take, if you take the expectation of this now, you'll find that it's equal to yt plus a naught s. Okay. So you will be able to forecast S periods into the future. Now, in contrast to the pure random walk model, okay, the forecast function is not flat. So here in the previous case, if you saw in the random walk model, if you forecast one period ahead, your expectation yt plus 1 will be equal to yt. Okay. If you forecast two periods ahead, it will be equal to yt again. That's what was shown earlier. Even if you forecast S periods ahead, this is the simple random walk model without a drift. So your forecast function is essentially flat. All your future predictions will be that the future values of yt will be equal to the last observed value. Okay? So because of this, if you're forecasting and graphing your forecast, then it will essentially be a sort of horizontal line and straight line. Okay? We'll see that when we are plotting our forecast also, if we have tomorrow's class. But here in this case, what you'll notice is that the forecast function here is not flat. Okay? Since in each period you have an accumulation of these drift terms. Okay? So because of this, the forecast function will keep varying by the amount A naught. Okay? Now using equation 13, okay, if you look at equation 13 itself, you can see that the mean, if you take the first difference of a random walk with drift, okay, then you will find that the mean is constant, it's equal to A naught. Then the variance will also be constant. Okay. Now if you look at the covariance again, okay, since here you get ET, this term, and this will be ET minus S. So the covariance is equal to 0. So because of this, all three conditions of stationarity are satisfied. Okay? Neither the mean nor the variance nor the covariance is dependent on time. So you'll find that delta YT, or the first difference of YT, is stationary. So if you have a random walk with drift model, if you take the first difference, then it becomes stationary. Now, if you look at this part, okay, now how do you remove the trend from a particular time series? Okay. Now, if you have a stochastic trend, okay, then you need to difference your time series. So here by differencing, it means taking the first difference or the second difference. So if a time series has n unit roots, then you need to difference the series n times to make it stationary. Okay? And in general, the dth difference of a process with d unit roots is stationary. Now in the random walk model, okay, there was one unit root. If you look at this, here in the random walk plus drift model, the coefficient of yt minus 1, okay, a1 is equal to 1. So here you have one unit root. Similarly, in the random walk, simple random walk model, again the coefficient of yt minus 1 is a1 is equal to 1. Okay, so this is also a case of a unit root. Since you have one unit root here, okay, so for a random walk model, if you difference the time series once, that makes the time series stationary, okay, which is what has been proved on the previous page. Now, suppose there were two unit roots, you would have to difference the series twice to make it stationary. So in general, the dth difference of a process with d unit roots is stationary. Such a sequence is said to be integrated of order d and is denoted by id. Okay? So the reason that it's said to be integrated of order d is if you perform the reverse operation of differencing, okay, or from a difference time series, if you perform the reverse operation, then you get back the original series. Okay? So that's why it's said to be integrated of order d, and this is denoted by id. So now if I write I1, it indicates that there is one unit root and the time series is integrated of order 1. So it needs to be differenced once to make it stationary. Similarly, if I write I3, it means that the time series is integrated of order 3. It has 3 unit roots and I need to difference the time series thrice to make it stationary. But in general, for most variables, you will not need to difference more than twice. Okay, so that's why in an ARIMA model, okay, you will find that AR refers to the autoregressive part, I refers to the integration, the order of integration, okay, whether the time series has been difference 0 times to make it stationary or once or twice. Okay. And the MA here in the abbreviation refers to the moving average components. So if you look at the general notation here, ARIMA PDQ indicates that the time series has d unit roots, and that's why it has been differenced d times to make the time series stationary. Okay. And then we usually model. For example, when you're taking the ACF and PACF, you'll use the difference series or make sure that your time series is stationary, and then you will plot the ACF and PACF. Okay. So an ARMA PQ process is difference stationary. So in general, if you have a linear deterministic time trend, okay, which was the first case we saw. For example, if you can predict that yt is going to change by a fixed amount, then we can use differencing to make the time series stationary. Okay. Sorry, the second case. Sorry, if not a fixed amount, if you expect yt to change by a naught. Okay, so here expectation yt is important. You're expecting that yt will change by a naught. Then you need to difference the time series d times in order to make it stationary if it has d unit roots. Okay. So here it's the case of a stochastic trend. So because of this, you need to difference the time series to make it stationary. Okay. Now you will take up detrending if there's a linear deterministic time trend. So if your trend is deterministic in nature, then you will remove the trend component from your time series, and that will make the time series stationary. Okay. Now in general, for a time series, you can estimate a linear or a non-linear trend. Okay, this is the usual practice which is followed. In our case, when we did the practicals, we decomposed the time series using moving averages, and from there we extracted the trend, and we used that trend to detrend the time series. Okay. But in general, this practice is followed. Either you estimate a linear time trend or a non-linear time trend, which means that you will have these polynomial terms, t raised to the power 2, 3, 4, and so on. Okay. Now, depending on a plot of your time series, you'll be able to determine whether you should use a linear or a non-linear trend. And if you are still doubtful, what you can do is estimate a non-linear time trend and then check the significance of these coefficients. Okay? So if you find that any of these coefficients are insignificant, for example, if A2, A3, and so on are insignificant, then you will drop them and simply use a linear time trend. Instead, if you find that A2 is significant, A1 is significant, but A3 is insignificant, and then in that case, you will use a quadratic time trend to estimate the trend and then remove the trend from your time series. So in order to detrend, generally you subtract the estimated values of the YT sequence. So you'll be subtracting this, okay, this entire component, which basically gives you YT hat. So YT minus YT hat will give you this error. The estimated error is ET hat. Okay, so that will be your detrended time series. So by removing the trend, okay, you should be able to get a stationary time series, which will be captured by these error terms. So just remember that this is the general rule, okay, that if you have a stochastic time trend in your time series, then you need to difference your time series. Okay, take the first difference or second difference until it becomes stationary. Instead, if you have a deterministic time trend, what you can do is eliminate the time trend by first estimating the trend using linear or non-linear methods, and then after that remove the trend. Okay. So you get the detrended variable that should be stationary, and you'll be able to model your time series using that. This is something that I've discussed in the previous class, so I'll just leave it open so y'all can go through it. Any doubts or questions so far? Okay, nobody seems to have any doubts or questions. We'll just take a quick break. Okay, it's 3:29. Let's just take a break for 5 minutes and we'll meet at 3:34. All right. Till then, I'll just leave that page open so you all can look at it. Right, I hope you all are back. Let's begin again. Okay, so now we'll be discussing how to check for stationarity itself, how to check whether a time series is stationary or non-stationary. So the first set of tests that we'll be discussing are known as unit root tests. So in the case of unit root test, the most famous of these tests is known as the Dickey-Fuller test. Okay, so here if you're given a first order autoregressive process of this form, okay, then simply subtract yt minus 1 from both sides. Okay, then you'll get delta yt is equal to gamma yt minus 1 plus et. So in this, what we need to test is whether gamma, which is equal to a1 minus 1. Okay, so the first order autoregressive coefficient minus 1. Okay, if we want to test the presence of a unit root, we are basically trying to test whether a1 is equal to 1. Okay, so this is equivalent to testing whether gamma is equal to 0. That's why we put the model in the form of equation 2 instead of estimating equation 1. Okay, so this is the idea behind the Dickey-Fuller test, that you manipulate or transform equation 1 in this way, okay, by subtracting yt minus 1 from both sides. And then instead of directly checking whether a1 is equal to 1, we check whether gamma is equal to 0. Okay, since the two forms are equivalent. Now the test was proposed by Wayne Fuller and David Dickey, okay, in a couple of papers. Now three alternative formulations can be used to actually test for the presence of a unit root. Okay. So the first is the simple case of a random walk. Okay. So here you'll simply be regressing yt on yt minus 1 and et. Okay. So there's no intercept term here at all. Now the second formulation is where you include a drift term. Okay. So a naught here is your drift term. And the third formulation is one where you include a drift and a time trend. Okay. So based on which particular of these equations actually describes your time series, you can decide to test the alternative formulations. Okay. So if you plot your data and it looks like there's a time trend, okay, then you might want to use the third formulation, which is given in equation 5. So any of these can be used. Instead, if you think that your time series seems to follow a random walk, okay, there's no clear trend, there's no tendency to drift upward or downward in any particular fashion, okay, then in that case, you can simply estimate the first model given in equation 3. So just plotting your graph will give you an idea. Plotting your time series will give you an idea of which formulation you might want to try. Okay. Now the null hypothesis of this particular test is that gamma is equal to 0. So the null for the Dickey-Fuller test is that the time series is non-stationary. Okay. It has a unit root, or that it's an I1 process. Since if you look at the model, since it's looking at a first order autoregressive process, okay, so it's assuming that there's one unit root. So that's why the null is that the time series is an I1 process, or it has one unit root. Now the alternative hypothesis is that the time series is stationary, okay, which means that the absolute value of A1 is less than 1, or that gamma is less than 0. Okay. So this will mean that the time series is stationary, or it's an I0 process. Okay. So your null hypothesis for this test is that the time series is non-stationary, and the alternative hypothesis is that the time series is stationary. Now the particular test statistic which is used for this test, okay, it does not follow the normal distribution, and asymptotically it has been found to have that it does not follow the normal distribution, and it's not a standard distribution. So because of this, Dickey and Fuller have generated their own distribution and formulated critical values for this particular test, with which you will compare the test statistic from the test. Okay, so to calculate the test statistic, you will take the estimated value of gamma divided by the standard error of gamma itself and compare it with the appropriate value from the Dickey-Fuller tables, okay, to decide whether to accept or reject the null hypothesis. Now, generally with any software, you will find that the critical values are given. Okay, when you run the test, they'll generally give you the critical values with which you can compare the value of the test statistic that you've got. Or otherwise, if it's not given in any basic econometrics textbook, in the appendix portion, you'll generally find the Dickey-Fuller tables are there. Okay. Now, the critical values for gamma equals 0, okay, it will depend on the form of the regression, okay, whether you're using equation 3, 4, or 5. Okay, because if you're using equation 5, it means that you're losing more degrees of freedom since you're estimating more parameters. Okay, so the critical values will depend on the form of the regression that you're using and also the sample size that you are considering. Okay. Now, the appropriate test statistics, okay, are called tau and tau mu and this. Okay, so the first one, if you're using model 3, okay, so if you're testing the null hypothesis of non-stationarity using model 3, then you'll use or you'll compare it with the tau statistic. Okay. Instead of if you're using the model where you've included a drift term, then you'll be using the tau mu statistic. If you're using the model given in equation 5 where you've included the time trend also, then in that case you'll be using this statistic, okay, to compare the critical values. So if you look at the Dickey-Fuller table, it will give you separate critical values for each of these cases, again based on the degrees of freedom and the sample size that you're considering. Now, one important factor in all these tests is that these tests assume that the errors are independent, okay, and have constant variance. So basically, they're assuming that the errors are white noise and they're serially uncorrelated, that they have constant variance. And another factor to remember is that the Dickey-Fuller test, it considers only a single unit root, since it's assuming that the time series can be described best by a first order autoregressive process. Now, because of these factors, it was found that there could be problems with this test itself, with the Dickey-Fuller test. Okay. So in order to take into account the fact that there could be serial correlation in the error terms and the error variance could be heteroscedastic. Okay, it could keep varying, it might not be constant variance. So in order to take these factors into account, an alternative test was proposed known as the augmented Dickey-Fuller test. So this test was proposed by Sayed and Dickey in 1984. So these tests, the Dickey-Fuller test traditionally can be applied to time series that can be well represented by AR1 processes with white noise errors. Now, if you have higher order autoregressive processes, for example, if you have an ARP process or an ARMA PQ process, for which you're not sure what the order of the time series is. Remember that when you get the time series, you still haven't modeled it, so you don't know the precise order of the time series, how many AR components are there, how many MA terms are there, and so on. So because of this, in order to take into account higher order autoregressive processes and serial correlation and heteroscedasticity in the error terms, okay, the augmented Dickey-Fuller test or the ADF test was proposed. So here the modification that is introduced is that we are including lagged values of the dependent variable over here, okay, when we are estimating the model. So the lagged values of the dependent variable become one of the explanatory variables. And this helps to correct for serial correlation and heteroscedasticity in the error terms. Now, I haven't given the precise derivation of this. Okay, it will become a little complex, so I omitted the derivation. but just remember that it takes this form. Now you can also, in this particular equation, I've only included the drift term here. Okay, so you have A naught, but you can also include a time trend here. You could also have A plus A2T here and estimate the model. So it depends on which particular specification you feel best describes the time series that you are modeling. Okay, so if you think that there's no drift and there's no time trend, you could simply include only gamma yt minus 1 and these lagged values of the dependent variable. If you think there's a drift, then you can use equation 6. If you think there's a drift plus a time trend, then you can also add plus a to t to this particular equation and then estimate that model. So here gamma, since I haven't gone through the derivation, it might not be very clear what gamma is, but gamma is equal to this. Now just remember that if there is any unit root, then the sum of the AI terms or the sum of the autoregressive coefficients will be equal to unity. Okay, this is something that we discussed in a previous class. So because of this, if there's any unit root, gamma will be equal to 0 since the sum of the AI terms will be equal to 1. Okay. So here the null hypothesis of this particular test again is the same thing, that gamma is equal to 0. It implies that yt has a unit root, okay, or it's a non-stationary process. And the alternative hypothesis is that the time series is stationary. Now, if you look at the specification of the null and alternative hypothesis, what you'll notice is that this is a one-sided test. Okay, so far when we were looking at the significance of the coefficients estimated from ARMA models, we were looking at a two-tailed test. That's why I asked you to consider the absolute value of the t statistic. Okay, since it was a two-tailed test, but here since this is a left-tailed test, okay, you will find that you need to look at only the left tail of the distribution. Okay? And the critical values are also such that if you find that the value of the test statistic that you have got, the t statistic that you have got from your regression, if it is greater than the critical value, which means that if it is more negative than your critical value, then you will reject the null hypothesis. Otherwise, you will fail to reject the null hypothesis. Now the same critical values apply as in the case of the Dickey-Fuller test. Okay, so you'll be using the same set of critical values which Dickey and Fuller generated using simulation methods. Now this Dickey-Fuller distribution, it is slightly left skewed. Okay, so you'll find that there are in general more negative values compared to positive values. Compared to the t distribution itself, it's slightly more left skewed. Now, there are some important things that we need to keep in mind when we're considering these tests, DF, Dickey-Fuller and ADF tests. Okay. One is that the true order of the autoregressive process is unknown. Okay. We don't know exactly how many AR terms are there or how many MA terms are there. So the appropriate lag length, okay, when you're choosing the lag length for these terms, how many lagged values of the dependent variables you want to include, that choice has to be made very carefully so that the error term ET is serially uncorrelated. When you finally estimate your model, if you check whether you've specified the correct number of lags, one way to do that is to check the residuals from your model. They should be free from autocorrelation. Yes, they should be serially uncorrelated. And while selecting the lag length itself, there are different procedures which are recommended. So one thing you can do is select the lag length based on criteria like the AIC, SBC, and so on. Okay. So that is one method you can use. Otherwise, you can choose other economists recommend that you choose a very long lag length and estimate the model. Then if you find that up to lag, let's say you've included p lags, okay, of the dependent variable. So if all those p lags are significant, then you can retain those p lags in your model and you can assume that your regression is correct. You have chosen the lag length correctly. instead if you find that the last lag is insignificant, okay, or the last few lags are insignificant, then estimate the model again using p minus 1 lags, then check the significance, statistical significance of the lagged coefficients again, okay, and keep repeating these processes, this whole process till the last lag which is left is actually significant. Okay. So you can do that. It's recommended that you don't do it the other way around, which is that you keep increasing the lag by 1. Okay. So it's recommended that you don't do that. Instead, include as long a lag length as possible and then keep reducing it by 1 based on the number of insignificant coefficients. Okay. So these are different ways to select the lag length for the ADF test. What you will find is that for most software, the test itself selects the lag length, okay, using certain formulae. There are certain other criteria which can be used. So the test either selects the lag length that way, or you can specify how to choose the lag length. You can fix it at a particular value, or you can specify that you want to use AIC or SVC and so on. Now, the other thing which is important to note for the Dickey-Fuller test is that it considers only a single unit root. Okay. However, if a pth order autoregression actually describes your time series, then you know that your time series has p characteristic roots. Okay. And if there are d less than p characteristic roots, the series has to be difference d times to achieve stationarity. Okay. So in general, if your time series has d characteristic roots, you know that it has to be difference d times to make it stationary. Okay. In this statement, okay, one thing I think I forgot to include, if it has d minus p unit roots, okay, then the series has to be difference d times to achieve stationarity. Just make that correction if you're copying the notes, otherwise I'll make it later when I'm circulating the notes itself. Okay, now Dickey and Fuller have also provided some additional statistics, F statistics, which are called phi1, phi2 and phi3 to test the joint significance of the coefficients. Okay, so you can use phi1 if you're using a model with an intercept and you want to check whether the intercept should actually be in the model. Then you can test the null hypothesis that gamma is equal to alpha naught is equal to 0. Basically, gamma and the drift term are equal to 0. Okay. So when you're testing this null hypothesis, it means that the time series is stationary and that it should not include a drift term. Okay. So if you are estimating the model with the intercept or with the drift term, then you can use the phi1 statistic to judge whether your model is described well by a model which will not include the drift term. Okay. So basically the null hypothesis says that the data are generated by the restricted model where these restrictions apply. Okay. And the alternative hypothesis will be that the data are generated by an unrestricted model where these restrictions do not apply. Okay. Now you can use phi2 if you're estimating a model with a time trend and a constant, then you can use phi2. Okay. So Dickey and Fuller have provided critical values for these F statistics also. So you use the statistic phi2, compare it with the critical F value, and then determine whether to accept or reject your null hypothesis. Okay. Then if you want to check whether you should not include the time trend term, okay, then you can use the phi3 statistic. So this way, based on these different statistics, you can decide whether to include the drift term or the time trend term in your model. Now, how are these phi statistics calculated? Okay. It is done in the usual way how it is done for an F statistic. Okay. So you take the sum of squared residuals from the restricted model minus the sum of squared residuals from the unrestricted model divided by the number of restrictions you've imposed. For example, if you're using phi 3, then you are imposing 2 restrictions. Okay, so this will be equal to 2 divided by the sum of squared residuals of the unrestricted model. Divide that by t minus k, where k is the number of parameters estimated in the unrestricted model. Okay? So you can use this to judge whether you should be including the drift term or the time trend term in your regression, and also to check the non-stationarity of your time series. The critical values are again generated by Dickey and Fuller. You'll be able to find it with any software. Now we come to the next unit root test, which is the Phillips-Perron unit root test. Okay, so this test was again proposed to address the fact that the error terms might be serially correlated and they might be heteroscedastic in nature. While the ADF test uses parametric methods to deal with the serial correlation and heteroscedasticity in the error terms, if you remember, we are including lagged values of the dependent variable to correct for serial correlation and heteroscedasticity in the error terms. There is the Phillips-Perron unit root test. It uses a non-parametric method to deal with this particular problem related to the errors. Okay? So instead of actually modifying the regression equation itself, what Phillips and Perron did was they changed the test statistic which is used after the estimation. Okay? So to estimate the adjusted variance of the error terms, the authors proposed a particular formula. Okay? Now I'm not going into the details of the test statistic itself and what this entire formula means. Okay, it's enough for you to understand that again they are trying to address the issue of problems with the error terms. Okay, and they are essentially estimating the same regression, only the test statistic that they use has been modified here. Okay. It's a little more mind-boggling if I go into the details of it. That's why I've omitted it. But again, in any software, you will get the critical values, which are the same as the Dickey-Fuller critical values. Okay? So you'll be able to compare them and judge whether your time series is stationary or non-stationary. Now, problems with these unit root tests are that generally they have low power. Okay? So by power, we mean the probability of rejecting a false null hypothesis. So how often will you be able to reject the null hypothesis that there's a unit root when the time series is actually stationary? Okay, so power is equal to the 1 minus the probability of committing a type 2 error. Okay, so it's the probability of rejecting a false null hypothesis. So you'll find that with Dickey-Fuller tests, even with ADF tests and Phillips-Perron tests, okay, if you have a near unit root time series, it's very difficult for these tests to actually reject the null hypothesis of a unit root. So even though A1 might be close to 1, but it's actually less than 1, even in these cases, you will find that these tests report that the time series is actually non-stationary when it's actually stationary. Okay, so because of this, these tests are supposed to have low power, and these tests also find it difficult to distinguish between a trend stationary process, okay, which means that there's a deterministic time trend, from a drifting process. Okay, so if you have a process like a random walk with drift, it will find it difficult to distinguish these two time series. So because of this problem again, other tests were proposed over a period of time. Okay? And the most popular of these tests is known as the KPSS test to address this particular issue. So KPSS derives its name from the authors of the test or those who proposed the test. Okay, it was devised in 1992. So here the null hypothesis is different from the null for a Phillips-Perron test or a ADF or DF test. Okay, so here the null hypothesis is that the time series is stationary and the alternative is that it is non-stationary. Okay, now the test has been devised this way. that if you're given a time series which takes this form, okay, so AT is the constant term, this is the trend term, and this is an error term. Okay. Now the error term is I0, which means it is stationary, but it may be heteroscedastic. Okay, this is one particular feature of this test. Okay. Now AT itself, if you look at the constant term, it is in the form of a random walk. So your constant term is entering the equation or the time series in the form of an additive random walk. Okay. And the error term in this random walk function, it's assumed to be independently and identically distributed and normally distributed. Okay. So this error term is supposed to be well behaved or similar to a white noise process. Now the null hypothesis is that yt is trend stationary and the variance of et is 0. Okay? That is, at is a constant. So if the variance of et is 0, it will mean that expectation at is equal to at minus 1. Okay? It will be some constant. Now this test, okay, it is a one-sided right-tailed test because the null hypothesis and alternative hypothesis are being devised this way. So the null says that yt is a stationary time series, and the way the test has been formulated, it has been formulated in such a way that the error term which enters the additive random walk part, okay, that has a 0 variance, okay, which implies that at is constant. Now the alternative hypothesis is that yt is a non-stationary time series and that the error variance is some positive value. Okay. So in general, what your takeaway should be from this particular test is that the null is that the time series is stationary and the alternative is that the time series is non-stationary. And the non-stationarity stems in from this additive random component. Okay. So these are the tests of stationarity itself. Now compared to the other tests that we discussed earlier, for example, Dickey-Fuller, Phillips-Perron and ADF. Okay, this is called a stationarity test because of the form of the null hypothesis, whereas the other tests are referred to as unit root tests. Okay, because they are geared to detect the presence of a unit root itself. Now this might seem slightly confusing, but once we do the practicals, I hope you'll be able to understand better. Okay, so we'll begin with the practicals now. Any doubts or questions so far?
Excuse me, ma'am.
Yes.
Ma'am, it's little awkward, and I'm sorry to ask this, but may I know how are we gonna utilize this? I mean, there are a lot of equations that we have read so far, and a lot of implications around it. So how are we supposed to work with them, like for the exams purpose, particularly, if I may ask?
Okay. For the practical aspect, I think it's understood to you, right? How you'll be using it?
Yeah, like on R we are working it is fine, but if we come to the theory or pen paper part, what are we expected to memorize out of it, or just make it?
See, you won't be asked to memorize, but you might be given certain problems. For example, I might give you a random walk process, but I will not state directly that it's such a process. So you might be given, for example, numbers. Okay, so I might give you yt is equal to, yeah, in this case, it'll be yt minus 1 plus et, but you will be asked to maybe derive the conditions for stationarity and so on, or you might be given an AR2 process asked to find the variance, the mean of the time series and so on. Okay, since it's open book, it's a little tricky, and I myself am not very clear how I'll be devising or preparing the questions. Okay, since you all can easily, since it's open book, you can refer to all the notes and all the derivations are there, but you might be asked to find the general solution for a difference equation. Then you might be asked to solve a difference equation, or you might be asked to prove the stationarity properties or that the time series is non-stationary and so on. Okay, so it will basically revolve around these sort of things. These tests I will not be asking you, of course. Okay. This is just for your understanding.
Ma'am, one question, please.
Yes.
See, in these ARIMA models, what we're talking, we have not looked at a independent variable as such. We're only talking about, a variable autoregressive on itself,
Yes.
right? So, what my query is in economics, how many of these pure, models one can find, or is this a starting point of understanding, and thereabout, thereafter you introduce the independent dependent relations?
Uh, in many cases, what you'll find is that ARIMA models are good enough, and many people actually use ARIMA models to forecast things like sales and even stock prices and so on. But
Okay, let me give an
pure,
example.
yes,
Yeah, let's say you look at okay, inflation. Let's say in CPI inflation, I start looking at it and start building an ARIMA model around that,
mm,
right? So I will maybe you can fit it because it's after all a time series, and you can show that it regresses on itself, either first or second or third lags. But eventually, when you look at forecasting or whatever, you want to like establish a dependent independent variable relation so as to bring in a policy aspect.
uh, see, even one thing that you would have noticed is if, uh, for example, if the time series is an AR1 process where maybe the first order autoregressive coefficient is very high, for example, let's say 0.95 or something like that. So there's a lot of persistence in inflation. If I take the same example that you are taking, so my inflation at time t, let's say this month, is heavily dependent on inflation in the previous time period. So getting an estimate of that autoregressive coefficient itself will be useful, because I know that I maybe need to reduce inflation very rapidly. Otherwise, it will keep, what do you say, uh, persisting into future periods because of the high value of the autoregressive coefficient itself. So a simple ARIMA model itself might help you in this case. But to answer that question that you were asking previously, we do also have other formulations known as Arimax or Rmax models, where the X is for other explanatory variables, like you were saying. So you could also include other variables in your model other than the time series that you're considering itself.
Okay.
So we haven't discussed it. If you want, later on, once we've finished a couple more units, then we can come back to ARIMA and I'll discuss RMAX or ARIMAX at that point of time. But you can include other variables. For example, you can include exchange rates or the value of GDP, anything, foreign inflation. All these things can also be included, but that will be an Arimax formulation. But since I haven't covered that theory, we are take this as the starting point. Once you understand this, you'll be able to build more sophisticated models.
Okay.
Uh, the other person who asked the question, I think it was Rashi itself. I hope that answered your question.
Yes, ma'am, but it would be great if you can just help us with some questions. I mean, just particular questions, so that it would be great to us, because we are already very confused around subjects and all these things, and we are unable to
Okay.
find anything related to it.
Okay, fine. Yeah, I'll do that. And in my notes, I'm trying to cover as much detail as possible so that you don't have to refer to any other book or any other reference material. Okay, so
Yes,
I'm basically taking it from different places, so I might not be able to name exactly where I've taken it from. But basically, if you refer to the notes, you will not need to refer to any other material if you've been able to follow the content in the classes itself.
yes, ma'am.
So
But my
let's,
purpose was only for some question bank would help us to give us exact picture, like what are we expected, or are we, if in case we are interpreting something wrong out of words.
okay, yeah,
Ma'am, one again one small question.
yes,
When we talked about unit roots,
yes.
does having more than one unit root,
Hmm.
what does that typically mean? Does it mean having more than a 1 lakh significant lakhs, or
If
is
you
that a
have,
crude way of thinking?
mm, if you have more than one unit root in a time series, then you'll find that if you run any of those unit root tests, then the first time it'll show that your data is non-stationary. So then you'll take the first difference and you will run the unit root test again. So again, if it's showing you that there's a unit root or your data is non-stationary, it means that there is more than one unit root. So you'll have to take a second difference, keep differencing till you get a stationary series. Only then can you run your regressions.
Okay,
So you'll
exactly.
have
So
to,
sorry for interrupting. I'm saying, so if you're differencing, my question was actually related to this only. When you say you're differencing more than once,
hmm.
uh, why exactly are we doing? Because the second period lag is more important or equally significant as the first period lag. Is that what we are uh, looking at?
No. When you're differencing more than once, if you'll have to go back to the theory part that we discussed earlier. So when you're solving a difference equation, that I'll just go into it a little bit to refresh your memory. So when you're solving the difference equation, the solution to that particular difference equation will have two parts. There'll be a particular solution and a complementary function. So in the complementary function part, you'll be taking all the autoregressive terms. For example, yt minus 1, yt minus 2, and so on. You'll be bringing it to the left-hand side, setting it equal to 0. So you'll have yt minus a1, yt minus 1, minus a2, yt minus 2, and so on is equal to 0. And then you try and solve that particular equation, find out, you'll get one characteristic equation. You'll be writing that equation in the form abt plus abt minus 1 and so on. So once you solve that and find out what are the characteristic roots, basically you'll be finding out what the value of b is. So once you find out what the characteristic roots are, for example, if you have an AR3 process, so in that case, there will be three characteristic roots. Now, if any of those characteristic roots are equal to unity, it means that Did I get disconnected at some point?
Yes, ma'am, for last 5 minutes.
Oh God. Okay. Uh, See, basically, I don't know how much of it you heard, but did you all hear me talking about spurious regression?
No, ma'am. We lost you at. You said asked a question on about the number of times you difference and the relation to unit roots. You were talking about AR3 process, and then you got
Okay.
lost.
So, in general, I'll try and cover this topic in the next class. If you have two time series which are non-stationary, uh, let's say yt and zt, and if I run a regression with these two time series, if I regress yt on zt, then it's called a spurious regression. Okay, it might show that there's some relationship between these two variables, but actually it's a false relationship. So I'll discuss this a little more in the next class, but it will give me wrong results or wrong ideas in general. There are particular cases of co-integration where you can regress two non-stationary variables on each other this way. So we'll be discussing that a little later. But in general, if you use non-stationary variables for regression, it's considered a spurious regression. And if you have, let's say, d characteristic roots which are equal to unity in a particular time series, that will just tell you the order of differencing that you need to use to make your time series stationary so that you do not run a spurious regression. But it will not tell you anything about whether yt is dependent on lag 2 or lag 3 or anything like that. Okay, I'm not very sure about what you mean by that.
When we difference, let's say yt, uh, when we say first difference, we are
Yes.
basically taking yt and differencing it at one period less, yt minus
Yes,
yt minus
it'll
1.
be,
Right?
yes.
So, and when I do twice, basically I take one more period. So yt minus 1 minus yt minus 2.
No, it'll be yt minus 1, the first difference of that. So that'll become yt minus 1 minus, in brackets again, yt minus 1 minus yt minus 2. That
Yeah, will
becomes
that,
the second difference.
yes, but that is the second lag, right?
No, that's different. Suppose I took yt minus 2, that is the second lag, sorry, that is the difference at the second lag. That's similar to seasonal lag. For example, when we suspected that we need to do seasonal differencing, there we took yt minus 12 for monthly data. Okay, so that was a seasonal difference. If I have quarterly data and I take yt minus 4, that is a seasonal difference again. So depending on the season, otherwise if I just take yt minus 2, unless I'm using half yearly data, it doesn't really make sense. So if it's half yearly data, again, you can think that it's a seasonal difference or something like that, since there are two seasons in 1 year. But otherwise, it will not make sense. I hope that answered your question.
Yeah, I guess I have to work on this more to get some more intuitive feel.
Okay. I'll quickly just teach you all how to load the data. If you have your own data set, how to enter it. I don't think we'll have enough time for everything else. Okay? So we'll just enter or load the data that we have. And then after that, we can proceed. If we have a class tomorrow, then we'll continue. So either you all can follow me or you all can just watch. So if you have R, you can just use this command. If you open your R Studio, you can just use this command to empty all the variables or delete all the variables, the work that you've done previously. Okay. Now, what I want to do is load my
Excuse me,
own
ma'am.
data set. Yes.
I'm sorry to interrupt. I think you are not sharing your screen.
Oh, yes. Okay, now you can see it, right?
Yes, ma'am.
Okay. So just use this command to basically clear all the variables, make sure that your environment is empty. And then after that, you can import your data set. Okay, so I'll be using the data set which I had mailed you all, practical one. We'll just quickly do the basic stuff related to that data set. Okay, how you enter or load the data into your environment. So I've saved it in this folder. Okay, so just go to the folder, go to browse, then select that particular folder or wherever you've saved it. If it's on your desktop, you can use that. Okay. So I've saved it as practical one. This is the same data set that I had mailed you. Okay. So you can open this data set. Okay. Now once you have opened it, okay, wherever you see time, okay, change that to date. Okay, just click on this down arrow, change it to date. And here change this to numeric. Okay, RPI change it to numeric. Okay, so once the change has been made, you can just import your data. Okay, so once you've imported your data, you can see that it's appeared here so that you can view it. Now I'll just load a couple of packages. The same ones that we used the previous time. So I'm loading stats, then ggplot2. Since you have loaded it, already installed the package in the previous session, you will not have to install it again. So I've just loaded ggplot2, fpp2, then forecast, and t-series. Okay, so first we'll just load the data. I think we have just about enough time. We've loaded the data. We'll just declare that it is time series. Okay, so just create the variable here RPI. It's already there, but you need to declare that it's time series data. So use the command ps, then specify the name of your Excel file. Okay, so here it's practical1, R is prompting you. So give that as the name of your data file. Now within data one, okay, since there are two columns, your first column has dates and the second column has RPI. These are residential property prices. It's an index of residential property prices for India. Yeah, and if you look at the frequency of the data, it's basically quarterly data. So here, just specify that RPI is in the second column. That's the time series that you're interested in using and analyzing. Okay, so you specify that your data is in the second column this way. Okay, so the first number is basically the row. You're just putting a comma to indicate that you're not specifying the rows, only the columns. So it will consider all the rows and the second column of your data set. Then after that, just tell R when your time series is starting. It's starting in the first quarter of 2009. Okay, so that's what I've specified here. Then frequency is 4. Okay. So the frequency of data, since it's quarterly data, the frequency is 4. Okay, there are 4 time periods in a particular year. So specify the frequency and then hit enter. Okay. So now R has understood that your RPI is a time series variable, and then you can use various time series commands to actually estimate or analyze this data. Okay, so just plot your data. Okay, so you can see from your data that there seems to be some sort of an upward trend in the data. Okay, so in the next class, we won't do it in this class since it will take a lot of time. I think tomorrow, if it's possible, please let's have a class so that it's not further delayed till the next class. Okay, so another week will pass and I don't know how you all will do your assignment. So if possible, please let's have a class tomorrow. Here you can see that the data seems to have some sort of a trend. Okay, but we will not use the data in this form. It's likely to be non-stationary, okay, because of the fact that it's trending. Usually trending variables turn out to be non-stationary. So in the next class, we'll try and manipulate this data and bring it to a stationary form. So for here, we'll stop today. For today, we'll stop over here and just understand that this is how you actually enter your data or load your data in the R interface. Okay, so we'll stop here for today. We'll continue in the next class. Tomorrow, just let me know by 11 whether you all will be able to attend the class or not. Okay? You can mail me on that same mail ID through which you receive your notes. Okay? Any doubts or questions other than that?
Ma'am, when do we have to submit the assignment?
Has anyone actually started working on it? I asked you all in the beginning, nobody answered.
Ma'am, no, because right now we are in the middle of placement season, so
Okay.
everyone is busy in that.
Okay, then I think I don't have much choice. Tomorrow, let's have a class, all right? If possible, please attend the class tomorrow. Let me know by 11 if you all are willing to attend the class. And then we'll figure out what to do about your assignments. But I'll basically be willing to give you around 2 weeks starting from Sunday.
Okay, ma'am, we'll let you know.
Okay,
Thank you.
fine. So we'll meet, if possible, tomorrow. Let me know by 11, otherwise next week.
Ma'am, could you send a mail out if there is any change in the timing of the class or there is no class?
Yes, yes. Once they inform me, I'll
Thank you,
just
because I'm
send a
not in the
mail.
classroom. Whatever.
Yes,
Thank you very
yeah.
much.
Okay. I'll inform everyone whether we're having the class or not once the students have informed me. Okay. All right. Thank you. All the best for your placements.
Thank you, ma'am.
Thank
Thank
you,
you,
ma'am.
ma'am.
Thanks, ma'am. Good day.
You're welcome.